Hi, so in today's video I'll be covering Unit 1 of Edexcel AS Chemistry. In particular, we'll be looking again at the mass spectrometer and how to interpret mass spectra. And we will finish off this video with a brief introduction to the periodic table and the main trends that we need to be aware of. So let's quickly look at Dalton's atomic theory. So he's considered the father of modern atomic theory, and he used measurements of the masses in which elements combine to propose a hypothesis. Number one, that all matter is made up of atoms, and atoms are indivisible and indestructible. Number two, all atoms of a given element are identical in mass and properties. 3, compounds are formed by a combination of 2 or more different kinds of atoms. And 4, a chemical reaction is a rearrangement of atoms. So Dalton sort of imagined that an atom is sort of like a spherical hard object, so like a marble, and the word atom comes from the Greek, which means uncuttable. And this theory formed the basis for understanding chemical reactions, formulae, and chemical equations, which allowed us to make huge advances in the 19th century. However, the accuracy of this atomic theory was questioned in the beginning of the 20th century, where J.J. Thomson discovered that all metals, when heated, give off identical tiny negatively charged particles, and he was also able to measure their mass-to-charge ratio. Another scientist called Millikan measured the charge of these particles, which meant that he was also able to calculate the mass. We call these negatively charged particles electrons. Later on, the discovery of radioactivity and also the separation of radium from the uranium ore, which was carried out by Marie Curie, led to the knowledge that alpha particles are helium atoms that have lost 2 electrons. So this led to the experiments of Rutherford and Aston. So Rutherford, he bombarded a gold foil with alpha particles, like shown here. So we've got the gold foil, and alpha particles are bombarding the gold foil. And the results of this experiment led to the proposition of the nuclear theory of the atom. And the main points are that an atom contains a small central positively charged nucleus. The diameter of the nucleus is very small compared to the size of the atom. It means that if an atom were the size of a football, the nucleus would be smaller than a full stop on this page. All the mass of the atom is concentrated in the nucleus, and the electrons orbit the nucleus. So Aston went on and invented the mass spectrometer, which allowed us to measure the masses of atoms precisely. And he made a very interesting discovery that not all atoms of an element have the same mass. So this is what we now know as isotopes. So you might say, well, why do we bother with this historical overview? Well, the development of the understanding of the atom from Dalton to Rutherford and beyond is an example of how science works. So a theory is first suggested, which is based on experimental evidence, and then that theory is modified steadily as more evidence is obtained. So for example, during the last 50 years, many more subatomic particles have been discovered, such as mesons and neutrinos. So for example, both of them are produced as a result of radioactive decay. In terms of neutrinos, they can also come from a nuclear reaction. Okay, so let's quickly look at the key definitions. So first of all, the atomic number, Z, which is the number of protons in an element, which is usually, in the periodic table, it's usually a number which is above the element, the symbol of the element, so here, which is the number of protons. Mass number A, which is found at the bottom of the element, tells us the number of protons and neutrons of that element. Relative atomic mass is the weighted average mass of an atom of that element compared with 1/12 of the mass of a carbon-12 atom. So relative atomic mass, the key thing to remember is the weighted average as compared to 1/12 of a carbon-12 atom. Relative isotopic mass is the mass of an atom of an isotope compared with 1/12 of the mass of a carbon-12 atom. And we mentioned previously, isotopes have the same number of protons, so they have the same atomic number, which is this one at the top. But because they have a different number of neutrons, they have a different mass number, which is at the bottom here. And the last definition is the relative molecular mass, which is the weighted average mass of a molecule of a compound compared with 1/12 the mass of a carbon-12 atom. Let's now look at the mass spectrometer. So as I've already mentioned, we can use this to measure the masses of atoms, molecules, and fragments of molecules. So this is sort of a diagram of what goes on inside a mass spectrometer. So first of all the air in the spectrometer is pumped out. A sample of the element or compound is injected. It has to be in the gaseous state. It is then bombarded with high energy electrons from an electron gun. So the energy from bombarding electrons strips electrons from the atoms or the molecule, forming positive ions. I'll talk more in detail on the next slide. So then once we've created these positive ions, they are accelerated by a high electric potential, and they pass through slits and emerge as a parallel beam of ions, as shown here. They then are deflected by a powerful magnetic field, as shown here by this magnet. So those with a greater mass are deflected less than those of a smaller mass, so which allows us to sort the ions according to mass. And also the angle of deflection will depend on the strength of the magnetic field and the mass to charge ratio of the ion. And the ions of lowest mass are detected first. The magnetic field is gradually increased, and the ions of greater mass are then detected. So the detector here is usually coupled with a computer, which will calculate the mass to charge ratio of each positive ion, and also it will calculate the relative abundance compared with the most abundant particle, and it then converts it into a percentage for each positive ion, which we then view as a mass spectrum, which we'll talk about in a minute. And this is what a modern mass spectrometer looks like. So in a lab, this would be the machine that we would be using. So here again, I've written out all the stages of mass spectrometry. The key things to know, so we might sometimes be asked to write out to represent when the gaseous sample is stripped of electrons to form positive ions. So the general formula is that we have a sample A, which is in the gaseous state, plus energy, which are the electrons from the electron gun, and we produce a plus, again, which is gaseous, plus an electron. And here's an example of chlorine. So first of all, chlorine to gas. Chlorine usually comes as a diatomic molecule, so when we bombard it, it first becomes Cl2 plus in a gaseous form, but it can then also fragment into Cl plus or just Cl. So it can be one is neutral and one is charged. So that's what we call as fragmentation. So again, you can read through this. This is just a reminder. So I made a little summary sheet of mass spectrometry. So the main stages are ionization. So we have to, if we have a solid sample, we have to make sure that it's ionized into a gaseous state. Then we bombard it with high energy electrons from an electron gun to produce positive ions. Then those positive ions are accelerated by an electric potential. Then they're deflected by a magnet, and finally they're detected, and we can then use the data from the computer to analyze the sample. And remember that they're always positive ions, also known as molecular ions, and they can be positive molecules, positive atoms, or positive fragments of a molecule. So they're always positive. Okay, so let's look at interpreting of the data from the mass spectrometer. So we can use the information that the computer calculates to find the relative formula mass. So, and the easiest way to look at this is the heaviest ion, so the one with the greatest mass to charge value, which is shown here, which is 72, is likely to be the molecular ion. And it's very few compounds have a mass spectra which does not contain a molecular ion peak, because all the molecular ions break into fragments. So, for example, here we have pentane, and the heaviest mass to charge value is 72. So this represents the largest ion going through the mass spectrometer, and we can be, it can be reasonable to assume that this is the molecular ion. Therefore, the relative formula mass of the compound is 72. So that's quite straightforward. So let's look at mass spectra of elements. So here I've got an example from this mass spectra. We can see that there are two peaks, one at 10 and one at 11, which tells us the relative isotopic mass. And the size of the peaks gives us the relative abundance. So we have boron 10 is approximately 23 and boron 11 is 100. So how do we find the relative atomic mass? So remember from the definition, that's the weighted average. So it's quite an easy calculation. So in total, we have 123 atoms because of the relative abundance. So we add those two together and we get 123. We know that 23 are boron 10 and 100 are boron 11. So to get the total mass, we multiply 23 times 10 plus 100 times 11 and we get 1,330. But remember that RAM has the weighted average. So in order to get the average, we have to divide the total mass by the number of atoms, which gives us 10.8. So the relative atomic mass of boron is therefore 10.8. So let's look at something a little bit more complicated, which is chlorine. As you can see, there is quite a few more peaks now, and I thought we could answer these questions while explaining it. So the first question is, explain why there are two separate groups of peaks. Well, chlorine goes into the mass spectrometer as a molecule, so Cl2. The ionization of these gives the lines at 70, which is this one, 72 and 74. But the Cl2 plus ions aren't very stable. So some of them split to give a Cl plus ion and a chlorine atom. So the Cl plus ions give lines at 35 and 37. So that's why we have two separate groups. B, state what causes each of the 5 lines. So 35, as we've already said, is the Cl plus ion. The 37 is the other isotope, which is the chlorine 37 plus ion. Then we have 70, 72, and 74, and that's just the combination of the two different isotopes. So the 70 peak is when chlorine 35 and chlorine 35 combine. Then we have 72 when we have chlorine 35 and chlorine 37 combining. And the last peak is when we have chlorine 37 and chlorine 37 combining. So that's why we have these different peaks. Question C, explain the approximate relative heights of the lines at 35 and 37. So 35 and 37. So we can see that chlorine 35, which is this peak here, is approximately 3 times more abundant than chlorine 37, because I don't have a ruler, but we can see that this line at 37 is about 3 times of that height. So it just means that chlorine 35 is more abundant. D, what are the approximate relative heights of the lines at 70, 72, and 74? So 70 is the highest one, and then 72 and 74. So we can assume that 74, let's say, represents 1 unit, so that can be 1. How many of these lines at 74 can go into the next one? So we'll see 1, 2, 3, 4, 5, 6. So about 6. And into 72, so 6, 7, 8, 9. So that's the answer for that. That lines at 70 is 9, 72 is 6, and 74 is 1. And the final question, why can't you predict the relative heights of the two clusters of lines? Well, there is no way of predicting what proportion of the Cl2 plus molecular ion will split up to give the Cl plus ions and the chlorine atoms. Okay. And the final question is calculate the relative atomic mass of strontium. So sometimes you might not be given sort of the graphical representation, you can just be given the mass to charge ratio and the percentage abundance. So how would we calculate the relative atomic mass here? So in this case, because we only have 1 plus ions, and the MZ value tells us the relative isotopic masses, which is these here. So if we add all these numbers together, we get 100%. So that is our total number of atoms. So we have 100 typical atoms. So to get the total masses, we need to multiply each of these by the percentage abundance. So we do 0.56 times 84 plus 9.86 times 86 plus 7 times 87 and 82.58 times 88. So the total mass that we get is 8,771. And because, as we remember, relative atomic mass is the average, so we need to, in order to get the average, we need to divide the total mass by the total number of atoms, which is, so the total mass is 8,771, and we have 100 atoms. So when we divide the two, we get 87.7, and 3 significant figures are sufficient here. So, and the final bit about mass spectrometers that the specification asks for is to describe some of the uses of mass spectrometers. So, first of all, it's used in drug detection. For example, when analyzing urine samples. So, let's say during the Olympics, all the athletes would have to undergo anabolic steroid testing. And because each anabolic steroid has a unique molar mass, when you take the urine from the athlete, and we use a low-energy mass spectrometer for that, the urine sample is vaporized and the steroid molecules become charged. So we can then compare the mass to charge peaks from the sample to the known value of a specific anabolic steroid, and if they match, then we can say that the athlete has used steroids. So that's quite a useful way of detecting drugs. Another use of mass spectrometers is in the pharmaceutical industry, where these are used to identify new compounds. And we have to use a low-energy mass spectrometer because a lot of the times the molecules are fragile, and the low-energy mass spectrometer will prevent the decomposition of those. And finally, we can also use a mass spectrometer in carbon-14 dating. So the relative amounts of the isotope carbon-12 and carbon-14 in a sample can be found using a mass spectrometer. Because carbon-14 is radioactive, its activity halves every 5,730 years, and it changes to nitrogen-14. So Newland first suggested that there was a repeating pattern of properties every 8 element, so that was known as the law of octaves. And this is what we now know as periodicity. We'll talk about periodicity in more detail later on. And periodicity basically refers to the fact that there is a pattern of regular repeating physical and chemical properties. However, it was ultimately Mendeleev, who was a Russian scientist, who produced the first periodic table, and which led us to the understanding of the fundamentals of chemistry that we have now. So the vertical columns are known as groups, and all elements within a specific group have the same number of electrons in the outer shell. So for example, group 1 elements such as sodium, lithium, potassium have 1 electron in the outer shell, and for example group 7 elements have 7 electrons in the outer shell. Then the horizontal rows are known as periods, and all elements in a period will have the same number of orbits. So for example, the third period, going from sodium to argon, will have an electron in the first, second, third orbits. And the blocks that we need to know are S, P, D, and F. So here are the different blocks of the periodic table. So the P block, which is here on the right, contains the elements in groups 3 to 7 and group 0. Group 0 is this one here, which are the noble gases. So neon, argon, krypton, xenon. A p block element has its highest energy electron in a p orbital. So the last electron added goes into the p orbital. We have the d block, which is shown here in yellow. A d block contains the elements scandium to zinc in period 4, so this period here from scandium to zinc. A d block element cannot really be defined in terms of energy because the energy level of the d orbitals is altered by the presence of electrons in the outer s orbital. So it can only be defined in Aufbau terms, so the last electron added to the d block element goes into the d orbital. And we'll talk about this in more detail when we look at transition metals. That's, I think, Unit 4 of Edexcel. And then we also have the F block here. We don't really need to use these because most of these are radioactive, so we don't really cover these. And sorry, I forgot to mention the S block, which is here, which consists of the elements in groups 1 and 2, so group 1 and 2. And an s block element has the highest energy electron in an s orbital, which means that the last electron added goes into the s orbital. The electronegativity of an element increases from the left to the right, as shown by this arrow here, and it decreases down a group or increases up a group. So first of all, what is electronegativity? What that is, the tendency of an atom to attract electrons towards itself. So the most electronegative element is fluorine, which is shown here in group 7, and the least electronegative element is cesium, which is here in group 1. And even though the noble gases are shown here, electronegativity does not apply to noble gases because they have a fully filled outer shell, so they're very unreactive. As we've already discussed, the forces that act on electrons are electromagnetic. Therefore, they obey Coulomb's law, which states that the magnitude of the force between two charged objects is directly proportional to the product of their charges and is inversely proportional to the square of the distance between their centers. So the three main rules that we need to remember is that opposite charges attract and like charges repel. Bigger charges means that there is a stronger force of attraction, and the larger the sum of the radii of the particles, the weaker the force. So the further away the two centers are from each other, the weaker the force between the two. Electrons are attracted towards the nucleus because it is positively charged, and the larger the atomic number, which is the number of protons, the stronger the attractive force. The electrons that are further away from the nucleus are less attracted than the electrons that are closer to it. And because electrons are negatively charged, they repel each other. Effective nuclear charge is the net charge on the nucleus after allowing for the electrons in orbit around the nucleus shielding its full charge. If we look at period 1, which includes hydrogen and helium, we know that hydrogen has a nuclear charge of +1, and it has 1 electron in the 1s orbital. Therefore, there is no force of repulsion, so the electron feels the full force of attraction of the +1 nucleus. The helium atom has a charge of +2 because it has 2 protons, and it also has 2 electrons in the 1s orbital. So, because these 2 electrons have the same negative charge, they're repelled slightly, and this results in that the net force of attraction between the nucleus and each electron is slightly less than that between a +2 charge and 1 electron. So the helium nucleus is said to have an effective nuclear charge of slightly less than 2. So let's look at period 2. Lithium has a nucleus that has 3 protons, so it has a charge of +3, and it has 3 electrons, 2 in the 1s orbital and 1 in the 2s. So the outer electron, which is in the 2s orbital, is repelled by the 2 inner 1s electrons. This means that the nucleus is shielded by the inner electrons, and the effective nuclear charge is approximately +1. So how do we calculate the +1 charge? So this is done by minusing the 2 negatively charged inner electrons from the +3 charge of the nucleus, which gives us an ENC of +1. For beryllium, the nucleus has a charge of +4, and there are 2 1s electrons shielding the nucleus, and then the 2s electrons also repel each other slightly. So the effective nuclear charge is not exactly +2, it is slightly less than +2 because of the extra repulsion by the 2 electrons in the outer orbital. Effective nuclear charge in a group, so because it's acting on the outer electrons of an element, really varies, hardly varies, and this is because the nuclear charge and the number of inner shielding electrons both increase by the same amount. So, for example, let's look at the example of sodium and potassium. So sodium has a +11 charge in the nucleus, then it has 2 electrons in the first shell, 8 electrons in the second shell. So in total we have 10 electrons. So minusing those 10 electrons from the +11 nuclear charge, we get +1. Potassium has 19 protons, so it has the nucleus has a +19 charge. It has 2 electrons in the first shell, 8 electrons in the second, and 8 in the third. So which means that it has 18 electrons. So to get the effective nuclear charge, we minus the 18 electrons from the charge of the nucleus, which gives us a +1. Size of atoms. So across a period, the trend is for the atomic radii to decrease, and this is because the greater nuclear charge increases the force of attraction on the electrons, which draws them closer to the nucleus. And this is slightly offset by the increased repulsion of the electrons from each other. So the net effect is decrease in radius, as shown here. And when we go down a group, the atomic radius increases because we're adding electrons. So we go from 11 to 19 to 57, and obviously the nucleus are shielded by the inner electrons, so the electrons aren't pulled in as closely together. So what about the size of positive and negative ions? So the general rule is that positive ions are always smaller than its neutral atom. When we're forming a positive ion, we're losing electrons. Therefore, the radius becomes smaller because the remaining electrons are now pulled in closer by the nucleus, and there is also less repulsion between the electrons. So when we have ions that have the same electron configuration, the ion with the larger charge will have the smallest radius. So in this case, aluminium 3+ will have the smallest radius because it has the largest charge compared to sodium and magnesium. So when we look at negative ions, they're always larger than its neutral atom, and that's because when we are forming an anion, we are gaining electrons. Therefore, there is increased repulsion between the electrons in the same shell, which causes the ion to expand until it's balanced again. So we can see here an atom neutral atom of sodium, and when it's positive it becomes smaller because it has now one less electron and there is less repulsion, therefore the other electrons can be pulled in closer by the nucleus, so they're more attracted, there's less shielding. With chlorine, we have a neutral chlorine atom of this size in green, and we can see that the Cl- is much larger, and that's because obviously it has gained an electron, so there is increased repulsion between the electrons, which causes it to expand to compensate for that newly added electron. So let's look at ionization energies. So the general definition of an ionization energy is that it is the energy required to remove an electron from an atom, an ion, or a molecule, and the units are kilojoules per mole. The first ionization energy is the first step. So it's the energy required to remove one electron from the ground state of each atom of a mole of gaseous atoms of that element. So this is the first stage. So we have a gaseous atom which is not excited, it's in the ground state, and so we're removing the first electron. So this is it's always positive, so the number in kilojoules per mole will always be positive because it's an endothermic reaction, and we represent it by writing, so for example for chlorine, so Cl in a gaseous form goes to Cl plus one electron. So because we removed an electron, we now have a more positive charge, therefore we're forming a cation. The second ionization energy is the energy required to remove one electron from each ion of a mole of gaseous singly charged positive ions of that element. The number for the second ionization energy is always positive, so again it's endothermic, and generally more energy is required because the electron that is being removed from a cation. So again, because it's positive, it's smaller than the original atom. So, and that's how we would represent it. So we would go from a singly charged cation to a 2 plus 1 electron. So successive ionization energies, they steadily increase, but they have big jumps sometimes, and that is those jumps in the value in kilojoules per mole is evidence of quantum shell existence. So for example, let's look at aluminium as an example. Aluminium has 13 electrons. This is the electron configuration here. So also remember, when we are removing an electron, we're always removing it from the outer shell. So the first electron to go would be the 3p1 electron. The big jumps for aluminium will be between the third and the fourth, which tells us that aluminium has 3 outer electrons and is in group 3. So the jump will be, so the first ionization energy is to remove this electron here. Second and third will be to remove the 3s2 electrons. So in total we're removing 3, and they're all in the same third orbital, but the big jump comes when we try to remove the 4th electron, because we're now into a new in the second orbital, so that shows us that there are quantum shells. In example 2 here of sodium, you can see there is a jump between the first and the second, and between the 9th and the 10th. So we can by looking at the jumps in the ionization energies, we can see that there is 1 electron in the outer orbit, and then there are 8 in the inner, because there are no big jumps. So we have 1, 2, 3, 4, 5, 6, 7, 8. And then there is another big jump, which means we're getting closer to the nucleus, and then there are 2 in the 1s orbital. So now that we've looked at the meaning of ionization energies, the syllabus also asks us to be familiar with the variation of the first ionization energies for the first 36 elements, so from hydrogen to rubidium. So the pattern from lithium, shown here in yellow, to neon is repeated exactly with the elements from sodium to argon. And apart from this insertion of the D block elements, this pattern is seen again from potassium to rubidium, which is here. So we can see that the general trend across a period is for the first ionization energy to increase. However, there are a number of slight variations that we need to talk about. So from this figure we can see that the maximum is the noble gas, so helium, neon, argon and krypton. And then minimum of each is a group 1 metal, so lithium, sodium. You see that across a period there is a general increase in the effective nuclear charge, which reaches a maximum at the noble gas, so from the group 1 as shown here in green, at the end of the period. This results in an increasing attraction for the highest energy electron and a general increase in the first ionization energy. So the group 1 element immediately after a noble gas, so for example after neon we have sodium, has its outer electron in the next shell of higher energy. So this electron is well shielded from the nucleus by the inner electrons. So the effective nuclear charge is close to +1 and the atomic radius is greater than that of any atom in the preceding period. Therefore, the first ionization energy of the group 1 element is lower than that of any previous element. So in period 2, the energy level of the 2p electron is significantly higher than that of the 2s electron because it is partially shielded by the 2s electrons. This means that less energy is required to remove the 2p electron from, let's say, boron, which is shown here, to remove the 2 electron, let's say, from beryllium, which is the next one up, so boron and beryllium. So for example, if we look at nitrogen here, it has an electron configuration of 2s2, 2s2, 2px1, 2py1 and 2pz1. And the next one, which is oxygen, has the electron configuration of 1s2, 2s2, 2px2, 2py1 and 2pz1. So the electrons occupying different 2p orbitals are further apart than the 2 electrons occupying the same 2p orbital. So when an oxygen atom is ionized, it loses one of the 2 electrons in the 2px orbital, as there is more repulsion between 2 electrons in this orbital than between the electrons in different orbitals. Therefore, it is easier to remove one of the paired 2p electrons of oxygen than to remove one of the unpaired 2p electrons of nitrogen. So the same arguments explain the discrepancies in period 3, where the first ionization energy of aluminium, shown here, is lower than that of magnesium, and the first ionization energy of sulfur is lower than that of phosphorus. So in period 3, there are dips after zinc and arsenic, which is zinc and arsenic here. So the electron configuration of zinc is argon 3d10 4s2, and that of the next element, gallium, as shown here lower down, is argon 3d10 4s2 4p1. So as the 4p orbital is at a higher energy level than that of the 4s or the 3d orbital, less energy is required to remove the 4p electron in gallium than it is required to remove one of the 4s electrons in zinc. So the reason why the first ionization energy of selenium, which is shown here, is lower than that of arsenic, here in group 5, is similar to the reason for the dip after nitrogen in group 2. So the definition of the first electron affinity is the energy change when one electron is added to each atom in a mole of neutral gaseous atoms. The value is usually negative, so it's exothermic, because energy is released when a negative electron is brought towards a positive nucleus. And electron affinity can be represented by this equation, so in the example of oxygen. So the first electron affinity of oxygen is minus 142 kilojoules per mole. So this is the energy change per mole. So this is how this would be written. Second electron affinity is the energy change when one electron is added to each ion in a mole of singly charged gaseous negative ions. So the second and third electron affinities are always positive numbers. They are endothermic. And that is because the incoming electron is repelled by the negative ion, so energy is required. You can also look at the variation of the first electron affinities of the elements, lithium to fluorine. So the electron is added to the outer orbit of the atom, and as an electron is negatively charged and is being brought towards a positive nucleus, energy is released. So the general trend is upwards because the atomic radii decrease from lithium to fluorine, which causes the force of attraction to increase. There is a dip at beryllium because the added electron goes into an already singly occupied 2s orbital. Therefore, it experiences a considerable repulsion and less energy is released. Another dip at nitrogen is caused by extra repulsion of putting a second electron into a singly occupied 2px orbital. So, and to finish off, I found this diagram which sort of summarizes the main trends of the periodic table. Thank you very much for listening.